Okay, I hope you all had a good lunch. Welcome back to the first session in the afternoon. And the session starts with a talk by Christoph Scholl on hierarchical stochastic SAT and quality assessment of logic locking.
Okay, thank you for the introduction. As already said, the talk is about hierarchical stochastic SAT and quality assessment of logic locking. My name is Christoph Scholl, and this work is together with my postdoc Tobias Seufert and master student Fabian Siegwolf. Now it works. Okay, thanks. I will introduce here the formalism of hierarchical stochastic SAT, or HS-SAT, and this is motivated by an analysis of logic locking techniques. And therefore, I will first introduce the background, logic locking, and quality assessment of logic locking. And it will turn out that the easier quality measures reduce to existing SAT-related problems. And but then I will introduce hierarchical stochastic SAT, and we have a prototype for solving this HS-SAT. I will shortly look into improvements, and finally I will give some experimental result in our application context, and I will give some conclusions. Okay, so for the background, logic locking in general has the goal of protecting integrated circuits from unauthorized usage. In the meantime, you have a globalization of the manufacturing of integrated circuits. And for this reason, the manufacturing is in many cases split between several companies and several places all over the world. And you can imagine that there is a design house which designs the chip and finally produces mask data for manufacturing. And but let us assume that the design house cannot afford to run an expensive fab. And therefore, there is a foundry which physically manufactures the chip based on those mask data. And since there is a split between several parties, there may be a trust issue between the various parties. And it may be the case that, for example, such an untrusted foundry does overproduction, which means it just produces more chips than ordered by the design house, and then it sells them on its own. And of course, this cannot really be avoided, but the design house wants to ensure that the overproduced chips do not work. And here, logic locking comes into play. And with this logic locking, you typically introduce additional inputs to the IC, which are called key inputs. And you introduce additional logic, which is typically connected to gates in the original IC and to the key inputs. And then you want to have that the IC only works when the correct key is applied at the key inputs. And of course, this key has to be kept secret. And here is a very tiny example to illustrate the method. Let us assume that this is the original circuit with 3 inputs, x1, x2, x3, and 2 outputs, y1 and y2. And then you select random lines or random signals in the circuit and introduce XOR gates and XNOR. okay, you're introducing XOR and XNOR gates. And for example, at this signal, you introduce an XOR gate, and at this signal, you introduce an XNOR gate. And of course, if you apply a 0 to this XOR gate, then you obtain the original signal. And if you apply a 1, then the signal is inverted. And here for the XNOR gate, it's the other way around, which means if you apply the key 0, 1 to K1, K3, then you obtain the original functionality of the circuit. And hopefully, if you apply a wrong key, then the functionality is changed. That's the idea. And now you come to the following scenario. The design house adds logic locking to the chip. And the foundry produces the chips based on the mask data, and it delivers the locked ICs to the design house. And then the design house stores this secret key in a non-volatile tamper-proof memory here. And this non-volatile tamper-proof memory is connected to, the key inputs. And in that way, the key is unlocked. And then the unlocked chips can be sold by the design house. Okay. And of course, the goal is that attacks against this logic locking method should not be possible. Or at least they should be too expensive to be realistic. This is rather the way I have to put it. And our attacker model here is that the attacker has only access to the locked IC. It doesn't have access, for example, to the netlist. And but it can buy an unlocked IC on the market. So it is able to find out the correct outputs by buying a correct IC, an unlocked IC on the market. So its only way to find out the key is by trial and error. And this has, of course, some weaknesses. And the first weakness I mentioned here is that not only one key is unlocking, but there are several keys which are unlocking. Probably also many keys are unlocking, or a large fraction of the keys is unlocking. If this is the case, then of course, it's pretty easy to find out the correct key by trial and error. Or a second weakness can be that there are many key patterns which are not completely correct, but almost. And I mean by almost correct that those key patterns produce correct outputs for almost all input patterns. And in this case, an attacker, which may be the foundry or an end consumer who has bought an IC which has not been unlocked, could just use this almost correct pattern, and for a long time no error occurs, and so it can use it. Okay, and so our goal is here. And what I have to say is that there are many different logic locking techniques around. So there many different logic locking techniques have been proposed. And here our goal is to provide quality measures for logic locking. And those quality measures should give us a precise quality assessment using formal methods. So there, in the literature, there are simulation-based methods for analyzing the quality of logic locking, but here we really want to have a precise answer based on formal methods. Okay, and as already said, our simpler quality assessment methods can be reduced to existing SAT-related problems, and in this context, we are always making use of so-called invited miter circuits, which are the following. Here you have, assume here, this is the original circuit. And here you have the locked circuit. And in this invited miter circuit, you will just combine the original circuit and the locked, and the locked circuit, and you connect the inputs here. And then at the outputs, you have a checker circuit. You just have a checker circuit which checks for a given input and a given key whether the outputs are all the same or not. It produces a 1. It produces a 1 if all outputs are the same. And if this is not the case, it produces a 0. This is the inverted mitre circuit, which I will use in the following. And now I come to a very simple first quality measure, which is almost trivial. This is key existence. A key is called unlocking if it computes the correct outputs for all possible inputs. And a very simple check would be to check whether there exists an unlocking key, which means you are asking whether there exists a key here, such that for all inputs here, there is a 1 at the output of this inverted mitre circuit, expressed here. And of course, this is a quantified Boolean formula. So you can reduce the key existence to a quantified Boolean formula. Okay, and a second, a little bit more complicated, but still easy quality measure is key uniqueness. And for key uniqueness, you are asking whether there exists a key different from the original intended unlocking key, K original, that unlocks the circuit. This is, of course, something you do not want to have. But of course, this can be reduced also to a simple quantified Boolean formula, or QBF. Okay. And in many cases, key uniqueness is not given in practice. So the ideal thing would be you have key uniqueness, but in many cases, this is not the case. And but this is also not too bad. If you don't have a large number of unlocking keys, then the trial and error attack is also not possible, or that the probability that an attacker finds a key which works is not that high. So we can modify, we can modify it in the following way to compute the fraction of unlocking keys just by replacing the existential quantifiers of key existence by a random quantifier. And then you get the fraction of unlocking keys. Here you're using a random quantifier with probability of 0.5. And a random quantifier, random p, is here defined as in stochastic SAT, which where the stochastic SAT formulas compute satisfying probabilities. So the semantics of the random quantifier is defined here in red. The probability of the satisfying probability of random px phi is just defined as you have to compute the satisfiability probability of the negative cofactor with respect to x and multiply this with 1 minus p plus the satisfiability probability of the positive cofactor, and you have to multiply this by p. Okay, and the remaining rules are simple. Here for a function which corresponds to 0, the satisfying probability is 0. For the one function, the satisfiability probability is 1. And for existential quantification, the computation of the satisfying probability reduces the maximization of the two cofactors. And for universal quantification, you have a minimization. Okay, I will come back to this later. Okay. So this looks like a stochastic SAT formula here. But if we compute just the negation, which is the fraction of keys which are not unlocking, then you see, and this is given in this formula, then you see this is actually just projected model counting. So a simpler version of stochastic SAT. Okay. And now I come back to the issue of almost unlocking keys. So what is if a key is almost unlocking? And for defining a measure using almost unlocking, I will first define the notion of the criticality of a key. The criticality of a key is just defined as the quotient of the number of key input assignments for which the key produces a correct output and the total number of input assignments. So the correct key has a criticality of 1, and the almost correct keys have a high criticality. And of course, we do not want to have keys different from the original key that have a criticality higher than some bound C, which is typically close to 1. And to check whether such a key exists, the existence of such an almost unlocking key can be reduced to the following formula. You can see here in red, this formula in red computes for a key which is different from the original key, just its criticality. In red, this is a criticality computation. And now this exists K does a maximization over all keys. And this maximum is compared to this criticality bound C here. Okay, so this exists a key with a high criticality. And this is a stochastic SAT formula, of course, as well. Okay, and now you can play the same game again. You can say, okay, a few keys with high criticality are also not too bad. And a first idea to find a quality measure for this our first idea was to compute the average criticality of all keys. Here you compute the criticality, and here you compute the average of all of the criticalities of all keys, and this reduces to model counting, as you can see here. But now, is this really what we actually want to compute? And if I'm asking like this, of course not, because I can give you 2 examples with average criticality of about 1/2. And in the first case, the original key has criticality 1, and all other keys have criticality of 1/2, leading to an average criticality of about 1/2, right? But this doesn't form any security problem because the keys with criticality of 1/2 cannot be used in practice because for half of the inputs, the output is correct. So you cannot use this key in a meaningful way. And the second case is 1/2 of the keys has criticality 1 and the other half has criticality of 0. This also leads to an average criticality of 1/2. But this forms a severe security problem because with a probability of 1/2, you can guess an unlocking key. So this shows that average criticality is not what we want to have. And for this reason, we looked into something different. What we actually want to have is to keep the fraction of keys with high criticality low. And the question is how to compute this. What you could do in principle, but which is not efficient at all, is we compute for each fixed key. There are many, but we could, in principle, compute for each fixed key, k fix, its criticality based on this formula. Okay, then you can compare this criticality with the acceptable criticality bound, which I call C. That means you check whether this expression is larger than C. Okay, and if you have done this for all possible keys, then you can, of course, compute the fraction of keys for which the comparison holds, which I call this is the fraction of keys with high criticality. And in the end, you can compare this fraction with an allowed value of D. Okay, and if you look at what we have done here is something like this. You have to solve a formula where you do a comparison with this criticality bound C somewhere inside the formula. And in the end, you compare with the whole result with this constant D. But this is something you cannot really express in a natural way in stochastic SAT. Therefore, we defined a new formula class, which is called hierarchical stochastic SAT or HS-SAT. And this is pretty similar to stochastic SAT with one difference. And the difference here is given here. In addition to the usual ingredients of stochastic SAT, we have an additional nested comparison here. If you have a stochastic, an HS SAT formula phi here, there may be a nested comparison which compares this formula with some constant Q, which is between 1 and 0. And yeah, this is the definition. And please note that Roland Jiang and his student Yue Fan also defined a definition which is pretty similar, very similar to this definition, independently from our work and in parallel to our work. And they came from a totally different motivation. But yeah, this has also been done this year. Okay, so this is the syntax definition, and now I will look into the semantics. And the semantics is pretty similar to stochastic SAT, but we just have to come up with a rule for nested comparisons. And here I will show the semantics based on our running example. The criticality bound here is 99%, and we compare with 30%. And what you can do is just you can represent this inverted mitre output as a function, and this function is represented as a decision tree, and the decision tree is built in the with variables in the order of this prefix here. And what you're doing basically is just a bottom-up evaluation of this decision tree. So okay, so for example, for the subfunction at this node, you are computing 1/2 times 0 plus 1/2 times 0 equal to 0, and so on. And okay, then on this level with the x1s, you compute the criticalities of key 0, 0, key 0, 1, 1, 0, and 1, 1. And what you have to do here is you are doing the comparison with this bound 99%, which means you turn this 0, where 0 greater or equal to 99% leads to false. You turn this to 0. You turn this to 1 because the comparison holds. You turn this into 0. You turn this into 0. And then we again have random quantifiers, and we go on as usual. So we compute the probabilities, and in the end, we obtain 1/4. Oops, problem here. And we compare this with our bound 30%. The comparison is false, and therefore the complete evaluation is 0. Okay, and based on this observation, it's immediately clear what we could do here as an algorithm. You could come up with a DPLL-based algorithm, or you could also look into an ROBDD-based algorithm, which we have done as a prototype. So what we are doing is we build an ROBDD for the matrix with a variable ordering according to the prefix of the HS SAT formula. Then we are doing a bottom-up evaluation of the ROBDD, similar to the decision tree, with two differences. There may be node sharing in the ROBDD, which corresponds to isomorphism reductions, and this just increases the efficiency. And there may be long edges, which correspond to Shannon reductions in the ROBDD, which also increase in efficiency, but they need special attention if they cross levels with nested comparisons. Okay, but basically it's actually the same as in the decision in the decision tree. Okay, so in the example, this is the BDD, and you're doing a bottom-up evaluation of this BDD, and finally you obtain the 0 as a result. Okay, I have to hurry up here a little bit. We have two improvements of the original method. First improvement is that we are using some flexibility with respect to the variable order, which means you have blocks and you are able to exchange variables inside those blocks without changing the result. This is one improvement. And the second improvement is present if you have matrices in CNF. And then you're doing basically semantic gate detection. And for this semantic gate detection, we are using the unique tool by Friedrich Slivovsky. And this semantic gate detection makes the CNF simpler, and you get rid of existential quantifiers. This is also an effect. And yeah, it needs some adjustment for the nested comparison. So the original definition doesn't work anymore, but this can be fixed. Okay, now I come to experimental results. First, for subclasses which are already known. And the quality measure here is average criticality. You see here, this is a model counting problem, and we did comparisons with the best solvers in the last model counting competition. And this is just to know how good it competes in our application context. And what you can see here, this is our tool. And here you can see D4 and SharpSat TD, and you can see that our tool, at least in our application context, solves more benchmarks. Okay, and this is the second quality measure, the fraction of not unlocking key, which is projected model counting. Here you see different result. Here you see that GPMC and Arjun-Ganak are better than our tool. And it is not the reason is not that the projected model counters solve more benchmarks than the model counters, but the reason is that our tool is worse for projected model counting than for model counting. That can also be explained by less freedom in the variable reordering process in the projected model counting benchmarks. Okay, here we have stochastic SAT, where it works also pretty well. And finally, we have hierarchical stochastic SAT. This is what we actually did here. And here you can see different options of the tool. One with logic synthesis and variable reordering before building BDDs. And this one is the best. You can read details in the paper. And okay, we did analysis for different methods in logic locking. And now I come to the conclusions. I introduce a new problem class, HSSAT, which is motivated by quality assessment of logic locking. By the way, this HSSAT problem is p-space complete, as already QBF and SSAT. And we presented the first ROBDD-based prototype solver and had first interesting results in our application domain. And also as a side remark, we can also provide benchmarks for subclasses of HSSAT if anybody is interested in them. Okay, future work, we want to improve our solver and we make more analysis in our application context. Okay, that's it.
Thank you. Any questions?
So hello. So I have a question regarding like there are SAT-based attacks which are able to break these kind of logic locking techniques,
Yeah.
right? So it was introduced in about 2015.
Yeah.
So do we have any measure to like measure how robust it is against those attacks? So particular logic
Yeah.
locking is
Yeah.
how much robust is
Yeah, I see.
against those?
What you're talking about are attacks which make an assumption which is not our attack assumption. Our attack assumption is that you do not have the net list. And those attacks were for the case that you do have the net list, and then you can use SAT to find out the key. But this is not our assumption. So we do not expect that we expect that the attacker may have only the chip or only the mask data, and extracting the netlist is difficult. But
Design is
but
not
but
there.
uh, but 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 it's an interesting point, because there are countermeasures against SAT-based attacks, and people came up with different logic locking methods which made SAT-based attacks impossible. And exactly those methods have properties like almost always almost unlocking keys. And therefore, this brought us to the idea to do this analysis, because people tried to avoid one weakness and introduce a second one. Therefore,
Thank
thank
you.
you for the question.
Yeah, please.
Hi.
I-
So I'm wondering if one could consider the reverse question of we are given this HSAT formula and one would like to synthesize the key circuit so that when you evaluate it, the HSAT formula is satisfied. You see how to synthesize this circuit and key?
uh, the key is not
Uh,
circuit, but it's just an input.
no, I mean the red part of your diagram.
Okay. The
This one, like, so you start with this green circuit
yes,
and then you added all these gadgets to generate the key, right?
yes. So this
Um,
is done by logic locking, yes?
right. So, and then you check a certain formula with all quantities and so on. So
Hmm?
I'm wondering, suppose I give you the formula that I want, and can you synthesize this red part of the?
Okay. I see what you mean. Your proposal is that you have a certain goal.
Yes.
You want to have keys with high criticality only 30%, and
Yes.
then you would like to come with an to come to a logic locking, automatic logic locking
Yeah.
method, which synthesizes something which fulfills this specification. Interesting question, but I have no idea how to do this. But yeah, that's interesting. Thanks.
Thank you.
Yeah, so we are running out of time. Maybe a very quick, maybe a bit of a follow-up question. If there exist non-unique keys, isn't that also a sign that the circuit itself has some kind of redundancy, and one could kind of make it smaller, and when you then do key locking, automatically the keys are unique?
Yeah. I'm not sure about this. It depends on the logic locking technique. In fact, we found out that for this very simple logic locking technique, randomly inserted XOR and XNORs, it's not too bad. And later on, there have been other approaches which made things worse in our view. For example, you can use testability measures as a guide where to insert the XORs and the XNORs. And you insert XORs and XNORs, for example, at points which have high observability. And then by inserting an XOR at such a point, you do not change the high observability of this of this signal, and then you insert another XOR at the same place, more or less. So in such approaches, there is a tendency to cluster the inserted XOR and XNOR gate, and exactly in those cases, you have many unlocking keys. So you have to look into the logic locking methods. Some have the vulnerability and some don't have it. Yeah.
Let's thank Christoph again. Sorry, let's take this offline. Okay. Next speaker is Friedrich Sliwowski, and he will speak about strategy extraction by interpolation.
The mic, oh yeah, it's on. So this is about relating a key notion in QBF research, which is strategy extraction, with a very well-studied concept in logic overall, and that's interpolation. So let me first explain what I mean by strategy extraction. If you have a propositional formula and you give that to a SAT solver, then you expect one of two things. Either you get a SAT answer, in which case you want a satisfying assignment, and most solvers are able to provide a satisfying assignment, or you get an unsat answer. And then these days you'll get a proof of unsatisfiability of that formula in one of the formats that exist. Now, given a quantified Boolean formula, and well, if you hand that to a QBF solver, then if the formula is satisfiable, you also want a proof, ideally. In many cases, the solvers can't yet produce them, but ideally, you'd want a proof. So because QBF is p-space complete, in the SAT case, we don't expect there to be succinct certificates like in SAT. And of course, in case the QBF is unsatisfiable, you'd also want a proof of unsatisfiability. Now, we know from QBF semantics that if the QBF is true or satisfiable, there exists a winning strategy for the existential player. That's what Martina called a model yesterday. If the QBF is unsatisfiable, if it is false, there exists a strategy for the universal player, or a counter model. And now the question is, given a proof of the QBF, can I efficiently construct a strategy from that? And that's what's called strategy extraction. And we say that a QBF proof system has strategy extraction or has polynomial time strategy extraction if, given the proof, you can construct a strategy in polynomial time. So asking or figuring out whether any given QBF proof system has polynomial time strategy extraction, that is a key question in QBF research. Like you want to understand whether the log of the solver operations can be understood as constructing a strategy. And as Martina pointed out, strategies, models, counter models are important in applications in many cases. So what do we know about strategy extraction for QBF proof systems? Let me briefly show you a hierarchy of QBF proof systems. This is not exhaustive, but these are some of the ones that have been studied. At the very top, there's G that we already heard about yesterday. This can also be used as a QBF proof system. And then there are many other systems here. For a range of them, we actually do have lower bounds. There are a couple of open cases here. But actually, for most of them, we do know that they have polynomial time strategy extraction. So all of these systems here, below this line here, so the only exceptions are QRED and G. For all of these systems, we know that they have polynomial time strategy extraction. only for Q-red and G, assuming that P is different from P space, we can't expect polynomial time strategy extraction. So in principle, on a theoretical level, this question is pretty much resolved for all proof systems that we're interested in. But if we look a little more closely at the systems that are actually used in practice, there are interesting differences, I would say. So these systems, these variants of Q resolution, these are the proof systems that correspond to quantified CDCL solving approaches. So these are solvers that try to lift CDCL to the QBF level directly. And for these proof systems, we have a very, very good strategy extraction algorithm that goes back to a paper by Valery Barabanov and Roland Chang from, I think, 2012. So this is these are linear time strategy extraction algorithms. So we really understand very well what strategies or what strategy a Q resolution proof corresponds to. And this particular idea has then been exploited in various papers on QBF proof systems, characterizations of the strength of Q resolution proof systems. So here, this linear time strategy extraction algorithm, and this also, in some sense, very easily understood strategy extraction algorithm was very important. So that is for quantified CDCL. One of the other main approaches, okay, so quick mention of QRED, which is also used in preprocessing, but I'm not going to talk about that now. What I want to talk about mainly is the proof system down here for all x plus res, which corresponds to counter-example guided abstraction refinement solvers. So these are solvers that try to take a QBF grounded in propositional logic and then call a SAT solver to solve it. And you'd want to do the grounding in a smart way so as to not get an explosion. And here we know less about strategy extraction. But let me explain what this proof system is using an example, and then I hope you'll understand how this works in general. So here's a quantified Boolean formula. We don't particularly care what the matrix is here. And what we can do here is write down all possible assignments of the universally quantified variables, which are U1 and U2, in a tree. We first branch on the possible assignments of U1 because this is the leftmost universally quantified variable, and then we branch on the assignments of U2. So we get this kind of tree here. And now so every node in this tree corresponds to a partial assignment of the universal variables. And now for each node here, we'll introduce a propositional variable representing the potential assignments of existential variables depending on these universal assignments. So E1 here is leftmost in the quantifier prefix. So the choice of E1 cannot depend on any universally quantified variable, right? So we'll just introduce E1 as a variable here. For E2, the choice may depend on the assignment of U1, right? So we introduce two variables here. One variable, E2 annotated with U1. This is supposed to represent the assignment that E2 takes under assignment when U1 is assigned true. And another variable, E2, not U1, which represents the assignment E2 takes when U1 is false, okay? And then, because E3 here is to the right of both U1 and U2, we introduce four annotated variables for E3. One where it's annotated with U1, U2 true for this branch. One where it's assigned, is annotated with U1, not U2, and so on, right? We get these four variables in the expansion for variable E3. And now we just go over all assignments of the universally quantified variables and plug in or substitute these variables over here for the existential variables. So if we take the assignment U1 false, U2 false, which corresponds to this branch here, we'll substitute, okay, for E1, we'll still use the variable E1. For E2, we will substitute E2, not U1. And for E3, we'll substitute E3, not U1, not U2, right? We do that for all four assignments of the universally quantified variables. And this is what we call the expansion of this QBF, right? Or a complete expansion of the QBF. This is now a propositional formula that is satisfiable if and only if the original QBF is true. And so it's unsatisfiable if the original QBF was unsatisfiable or false. If our QBF phi was in Prenix conjunctive normal form, so if the matrix was in CNF, then the expansion will also be in CNF. And now to get a proof system for quantified Boolean formulas, we don't want to create the expansion in one go because that in general will be exponentially larger than the QBF. But instead, we hope that a small subset of clauses in the expansion will already be unsatisfiable. And so we'll allow the proof system to just generate individual clauses from the expansion one by one. So we'll have a rule where we take an assignment of the universally quantified variable, sigma, and a clause from the matrix. So this is the purely propositional part here. And we'll assume that this universal assignment here doesn't satisfy the clause C. And then we'll generate the corresponding clause in the expansion, right? I'll use this notation for that. Okay. So again, this just means we plug in the universal assignment and we replace the existential variables with the right annotated existential variables. That allows us to create clauses in the expansion, and then we just need a propositional proof system to solve or to figure out whether the set of clauses is satisfiable. And we can use resolution for that. And this system is called, well, exp plus res for expansion plus resolution, because that's just what it is. Okay, what do we know about strategy extraction for these proofs? So first, here's an example of a for all x plus res refutation of a QBF. Our quantifier prefix, we have 4 clauses. Now, we can instantiate them using assignments of the universal variables. So here, this first clause, we will instantiate with U1 true, U2 false. And then we'll get the clause containing just E1. Because E1 is leftmost here, it's to the left of all universal variables. We don't annotate it. Then over here, we instantiate with U1 true, U2 true. And we get this clause here where, again, E1 is not annotated, but E3 is now annotated with that assignment, and so on. We get these 4 clauses. This gives us a subset of the expansion, and this is very easily refuted, but just by resolving the first 2 clauses and the second 2 clauses, and then resolving the results, right? So this is a resolution refutation of these clauses generated from the expansion. Now, there's a fairly high-level argument for polynomial time strategy extraction from these proofs. And the idea is that the universal player in the evaluation game can use the proof to choose the right move so as to falsify the QBF. Suppose the existential player, who in the evaluation game plays first here, chooses some assignment, let's say E1, E2 true, then we can just apply this assignment as a restriction to the resolution proof. This clause here becomes satisfied, this literal vanishes, and we just end up with these two clauses, and we get a refutation after restricting the proof. And now, because we've assigned all variables to the left of, or removed all of the existential variables to the left of E3, every annotated literal here on E3 has to have the same annotation in the proof. Because in the proof, only variables with the same annotation are treated as the same. And so all of the existential literals remaining in the proof have to have the same consistent annotation. And that's going to be the response of the universal player. Okay? And then we would just continue like that. In this case, the resulting formula is just, it's just, regardless of what E3 plays here, it's going to be, it's not going to satisfy the matrix. So these proofs can be used to guide the universal player in the evaluation game. And all of these operations are polynomial time, so you can turn this into a polynomial size circuit that tells you how to play. And that gives you polynomial time strategy extraction from these proofs. So that's one option. I don't know if there's a really good analysis of the complexity here, but it's certainly polynomial time. We tried to improve this a few years back using a very nice but slightly complicated semantics for QBF proof systems based on partial strategy trees. I'm not going to explain this in detail, but the gist of it is that you can represent clauses as partial strategy trees, and then you can combine these strategy trees in some kind of a product operation, and that gives you, that allows you to iteratively construct a winning strategy for the universal player, right? And we showed that you can actually simulate this fairly efficiently using circuits. So overall, we got a running time of m times n, where m is the number of clauses in the proof, and n is the number of universally quantified variables. I wasn't very satisfied with this result because we really relied on this rather complicated semantics for QBF proofs, and it didn't give us any real insights on what makes, or on how to, on what kinds of strategies expansion proofs represent. And because of these operations being global on the entire strategy tree, it's hard to really understand what an individual strategy function for an individual variable means here. So my goal was to find a more interpretable strategy extraction algorithm. And for that, interpolation came to the rescue. So interpolation is this very well-studied concept in logic, where if you have a formula phi that entails a formula psi, then an interpolant is a formula that sits in between these formulas. So the interpolant is implied by phi, and in turn implies psi. And moreover, the interpolant only uses the non-logical symbols that are shared by both formulas. So this was proven to, so such interpolants were shown to exist in first-order logic by Craig. It's a well-known result. And I think since then, it's been shown for many other logics that interpolants exist. In model checking, there's a formulation, model checking also, well, formal verification model checking also frequently uses interpolants. And they're a slightly different definition is used where we start from a conjunction of two formulas that are jointly unsatisfiable, and then an interpolant is implied by the first part, and it's unsatisfiable when conjoined with the second part. This is, and again, the shared variables are only the ones that are in both formulas. Okay, that's what's called a reverse interpolant. Now one can ask, given a specific propositional proof system and a refutation of such a formula, can you efficiently compute an interpolant from this refutation? If that's the case, the proof system is said to have feasible interpolation, and resolution is very well known to have feasible interpolation. So if we have a resolution refutation, we can efficiently compute an interpolant. One way of doing this is using what's called an interpolation system. So here's a simple resolution refutation and a bipartition into the phi and psi. So phi is over here, psi is here. And now to compute an interpolant, every clause will be associated with what's called a partial interpolant. So and specifically, the input clauses in phi will just get false, constant false as an partial interpolant. The clauses in psi are going to get 1 as a partial interpolant. And then for resolution steps, we also have rules. I guess I'm not going to go into that really. The important point here is that what we need to be able to tell here is for input clauses, whether they are in one part or the other part. And for derived clauses, we have to look at the pivot and be able to say whether that pivot variable only occurs in one part, or only occurs in the first part, only occurs in the second part, or whether it occurs in both parts. Okay, now people already understood that there is some connection between strategy extraction and interpolation. Sorry, how much time do I have? Okay. So suppose we have a propositional formula written as a QBF, which consists of two parts here that only share these X variables. Okay, and suppose this is false. So it's an unsatisfiable formula. We can turn this into a real QBF introducing a universally quantified variable just after the shared variables. And then we can disjoin this part with U and this part with not U. And now a winning strategy for the universal player, which now can only depend on the shared variables. This will tell us under any given assignment of the X variables, which one of these is false. So strategy extraction implies an interpolation in some sense. So if you can efficiently perform strategy extraction, then using this trick, you also get interpolation. And for individual universal variables, it was also known that the interpolant between the two ways of expanding here, so substituting 0 on one hand, substituting 1 on the other hand, that interpolant is a winning strategy for the universal player. So I'm not sure who first observed this. It's certainly in one of Roland's papers here. Okay, that's for a single variable. The problem, okay. So just trust me on this. The interpolant is a winning strategy. One can verify this. So going back to our running example, I was aware of this. I thought, okay, it would be nice if we could use interpolation also when we have multiple universal variables. And the idea is to, okay, first start with the first variable, do what I just suggested, and compute an interpolant between the part of the expansion or the set of initial clauses that was derived using assignments that contain not U1, and the part of the expansion that was instantiated with assignments where U1 is set to true, right? This gives me a bipartition of the axioms. And then I can just compute the interpolant using the, well, for instance, using this interpolation system. I'll go around through this a bit more quickly. That will give me E2 as the interpolant between these two formulas. Okay, and I'm saying, okay, that's going to be my strategy function for the universal variable U1. Now I was thinking, oh, maybe I can just do the same thing essentially for variable U2 and compute the interpolant between, well, again, the set of axioms that was instantiated using assignments where U2 is false, and the set of axioms that was instantiated with assignments where U2 is set to true. Okay, if you do that, you get, let me check, you get E1 as an interpolant. Okay, so that's great, but unfortunately, this is not a winning strategy because if you take the assignment that sets all of the variables to false, that's certainly consistent with this strategy, right? But if we look closely, every clause contains a negated literal here. So this assignment, which is consistent with our proposed strategy, will not lead to a winning assignment for the universal player. So that doesn't work. How can we fix this? Oh, I should say in another paper by Roland, this is where I took the example from essentially. And it kind of, yeah, ruined my evening, but ultimately was able to repair this idea. So yeah, quick remark here. If your proof has a particular structure, then actually you can make this work. But it requires a certain ordering on the pivot variables, and in general, you don't have that. Okay, what can you do instead? So again, take a QBF. If that's false, unsatisfiable, then the expansion is unsatisfiable. And now we can think of the expansion as consisting of two parts. Again, the part where the first variable was instantiated with false, and the part where the first variable was instantiated with true. Okay, okay, I'll speed up a little bit here. Great, so we already saw the interpolant tells you which of these two is unsatisfiable given an assignment of variable E1. Okay, so if the interpolant evaluates to false, then the first part is unsatisfiable. If it evaluates to true, then the second part is unsatisfiable. And the idea is now, okay, let's say we're in the unsatisfiable part here for U1. Now we want to, again, look at the bipartition of this part induced by the labeling with U2. Right, so there's a part in this part of half of the expansion where we instantiated with not U2, and a part where we instantiated with U2. Okay, want to compute the interpolant between these two parts, and that then will tell us which of these two parts is unsatisfiable. So that's in the case we picked U1 true, and we also want to be able to do that in case we picked U1 false. Okay, and we can, in principle, continue, and by always computing these interpolants. So what our strategy function should be is, if U1 is assigned true, we want to use this interpolant. If it's assigned false, we want to use the other interpolant. And the corresponding, if we continue like this, the sequence of these interpolants is going to be a universal winning strategy. Now the question is, how can you compute this efficiently? Because if you just try this, that's going to give you, you would have to go in each subpart and compute an exponential number of interpolants. So you can't directly use this. Can you say exactly how long I have? I'm done? Okay. Okay, sure. Including questions, great. Okay. So there is a way of just fixing the just modifying the interpolation system so that now instead of having a fixed bipartition, your bipartition depends on the assignment of the previous variables. Okay. You can just trust me on this one. You get a winning strategy if you follow that. Yeah. And we get the same running time we had before. I have experiments here showing that, first of all, these ideas work in practice, and it's okay. The interpolation one and the older one from 2020 implemented, they're both better than this game-based approach, but they're very similar actually. So the running times are very similar. And the strategy sizes here between these two approaches are also very similar. They're pretty consistently better than just the round-based approach. Okay, so I was able to come up with a strategy extraction algorithm that works just as well as the one that I proposed in 2020. Why do I still like this result? I think it's, on the one hand, it's more interpretable. But more importantly, I think because it uses interpolation, there are many ways of, or many routes for generalization. One should look into other interpolation systems. So now the result currently is specific to one interpolation system for resolution. One should look into more. There are other expansion systems that have been proposed. Or well, you can combine expansion with any other propositional proof system. Does it still work there, and under which conditions? There are more general instantiation-based proof systems one could try this with. And I guess most importantly, I think it also works for certain theories of quantified SMT. So and now that there's proof generation in SMT solvers, maybe that's something one could try. And there are a couple more ideas, but I'm not going to go into detail here. Thanks.
Yeah, maybe it's just one question, if there are any. Sure, ask as long as you want.
You made the interpolation actually to look like symmetric on this one example. So because you had these two sub expansion, and but it's not symmetric in this.
You mean the interpolation system? There's a symmetric one. There are other ones. Yeah. So the Macmillan's is not symmetric, but the one I used here is the symmetric one. Yeah.
Because of we are late, let's take further questions offline, and let's thank Friedrich again.
Right.
All right. So the last speaker of this session is Armin Bire, and he will talk about blocked clause elimination for projected model counting.
So this is the after lunch session. So let's start with a poll to make it maybe more exciting. Who of you ever taught DPLL in a class? DPLL? Oh, come on. All right, so half the room. That's what I expected. So what are the ingredients of DPLL? Like, this is now 70 years old. What would you show? Like, there's the two base cases, right? There's this split. There's unit propagation. One thing I did not explain yet. Pure literals, exactly. So this talk is actually about like an extension of making pure literal work. Okay. Because the fun part is that pure literals are actually not part of SAT solvers. However, they are in QBF solvers, if some of you know, and so you may wonder how they are implemented. And actually, like my student Florian Lonsing did this in depth QBF, and he did it in a very simple way. So you just watch a clause, which is a candidate for the last clause, which has a literal, and if this goes away, then of course you know that it's a blocking literal, right? Pure literal, right? Clear, right? Now, what's the data structure you need for that? Well, actually, you don't need any data structure because you see you have the list of all clauses in which a literal occurs, right? So you just need to have this additional one pointer for every literal to the clause which is not satisfied yet and contains a witness for this not being pure, right? Like kind of the opposite. All right, now Jean-Marie here, actually past postdoc, he's back in France, professor now, had this brilliant idea of doing a watching data structure for block clauses. And then this has many applications, and he's the author of this kind of projected model counter D4, right, which is very successful. So he put it in there and got remarkable results. And then at the end, I got an email, don't you want to help me kind of get related work correct and help me with the exposition? And that's what I did. So I'm kind of not really the main author here. So this is Jean-Marie. And this is also with Pierre Marquis, who was the original supervisor of Jean-Marie. All right, so I'm going to show you how now to dynamically do block clauses. And this is specific to projecting model counting because this is the application of Jean-Marie. But I think like this has many other kind of usages, for instance, in QBF, right? All right, so you know what projected model counting is. It's a generalization of standard model counting. It's at least sharp P sharp hard. It's more kind of challenging than sharp-sat. Why? Well, if you implement this, you need to kind of almost like in QBF, you need to kind of split, take the order into account of the projected variable. You need to split on the variables on which you split first. And this restriction makes it actually harder, okay, in practice. Now, Jean-Marie worked also before on preprocessing for sharp-sat, which is kind of the basic version here. And so the question was, can you kind of use preprocessing for also projected model counting? And block clauses seems to be a good candidate. Well, I mean, you would consider also variable elimination, but that's not that good. And also, Jean-Marie actually had a paper on this. So you actually can only eliminate variables which are defined, like are functionally dependent on other ones. So this is already existing. So the question is, can you do this with block clause elimination too? All right, so the setting is clear. So I just want to show you the syntax, what Jean-Marie, who did these slides. So sigma is our formula, or CNF, no phi, but like sigma. And then we have models, and clauses have Greek letters. So actually only going to use alpha as clauses. Then we do resolution, and we don't need to put the literal here at this point because, well, if it's tautological, right, then it will be tautological no matter on which literal I resolve. And if it's not tautological, there's only a single literal over which resolve. So this is resolution. And model counting, well, we're going to use this running example of a formula here on top. And well, you now need to believe me, actually need to believe Jean-Marie because I didn't check. So this thing has 9 models, but you can probably get the argument. And this is over sort of these variables here, right? And if you now do projected model counting and you kind of filter out in these 9 models, kind of those with this common prefix here, right? I'm projecting here on the axis. So I want to know how many models are there different in axis, right? Then you only get those 4. And this is kind of half because they're like 3 variables, right? All right, now to block clauses. And there, maybe you've been to my tutorial talk on Monday. So these block clauses go back to Oliver, who sits there, but like we used them in a completely different way than he used them in '99. So we used them as a kind of a new way of improving, let's say variable elimination. On top of that, we looked at mechanisms to remove individual clauses, right, to simplify the formula. This was in 2010, and back then, actually, we thought this will be really helpful and solve really SAT faster. And we had actually evidence this is true. Nowadays, if you, for instance, look at my solvers, it's all disabled because actually the solver gets slower if you do block clause. And it's really painful because we figured out these cool ways of making and implementing this so fast that it's like you can actually do it. So in SAT block clause does not help. Actually in QBF it still helps. And here also, but actually not in the way we used it originally for SAT, like pre-processing, but actually dynamically. So we were going to do this. This is why I told this story with DPLL. We're going to do these block clauses like while we're splitting, right? However, as I also pointed out on Monday, so these block clauses were the starting point of our journey into all these proof systems, right? So I would claim that without these block clauses, we now would not have these nice proofs because this was for us the starting point to do that. All right. So if you apply block clauses on this formula here, block clause elimination, then you can remove this clause, and now I need to remember why. I think like it was the x1 here. So if I try to resolve on this x1, right, I need to find here clauses which have not x1. So for instance, this one here, and this is the only one, right? Only one with not x, but it also has the negation of x2, which is the second literal. So if you resolve these two, you get a tautology. All right, and then this one goes because here the candidate will going to use this clause again is only this third one, right, with the y1 here, and they clash. This is also terminology, or then on this x1, right? So I can remove this clause here because this clause here has the negation. Well, and so on. So we're doing block clause elimination. You know this story, so we can continue doing this. Well, and we actually solved this formula because it's now SAT. And so how many models does this formula have? Well, I think it's 2 to the power. How many y's have I? Yeah, so it's 2 to the power 6, so 64, okay. And then projected on X, it would be 16, right? So clearly, block clause preprocessing does not preserve projected model counting. Well, if you think a bit about it, it's completely clear, right? So this doesn't work. Actually, there's an interesting note here in an LPAR paper from 2013. I just checked it this morning. Our first page on the bottom it was about block clause decomposition. Exactly, we call this a block set, like a set of clauses which can be completely eliminated by block clauses. And Marijn and I had the conjecture, which we later disproved, that if you have such a set which can eliminate by block clauses, can you compute all models, so not projected model? Can you compute all models in polynomial time? Because as some of you know, there's this reconstruction stack which almost serves as a circuit, and it actually kind of lets you fix a model for the original set in polynomial time. So the question is, can you actually use this to do sharp-SAT, right? It's a reasonable conjecture, but it's wrong. So anyhow, so we thought about this before, and in a certain sense, you see this paper by Jean-Marie is the first one which really made use of this block clauses. All right. But and you might actually already thought about this thing. So this is just says if you now have a variable in the projected in the part which is projected out, right? So our y variables, right? If we quantify over the y variables, then so here, yeah, so here it's called x, so maybe so we're quantifying over some variables, right? This is the projected part of projected model counting. Then, of course, you can eliminate this variable. This is completely due to variable elimination because this is just the semantics of projecting out. But you can also just remove block clauses, which if the clause is blocked on this variable. There's actually in model checking, there's a similar paper by I'm not sure Christoph was on that paper, but like from colleagues from Freiburg back in 2012. So that means if you're not interested in some part, then on that variables, which are the other interesting one, you can apply like lots of things. You can do block clauses. You can, and maybe you also know from SAT solver like practice. There's this freezing API call, and everything which is not frozen, you're allowed to do with the SAT solver what you want. And this is in a certain sense what we have here, right? Okay. Now, what we so we saw it in the first example. So we cannot blindly do it. We can do it sort of on these variables which are eliminated anyhow. So, but now how do I do this in practice? And this is sort of the nice insight of Jean-Marie. He found also watching mechanism similar to the one I explained for pure literals, but it needs a little bit more work. And then the additional data structures, the real core here is I think is the next slide, is the data structure for the watches, right? How do you update the watches, and how you need to compute something actually in addition, because obviously only the occurrence lists don't work. So this is the real key contribution. So here once again we have this blockness definition, and what we want here, we want to have a mechanism. So this is kind of in this block clause manager, and this one is added to the D4 DPLL style method for model enumeration, for model counting, which is backtrack free. So you want to get sort of like a as with the other one I explained for pure literals, you want to backtrack and then don't need to update anything of this manager. Okay, and there, of course, the main insight is that you find sort of witnesses that a certain clause is not blocked, right? So when can you not remove a clause on a certain literal, right? When is clause not blocked on a certain literal? Well, if there's a resolution candidate, this is now alpha prime here, which on that, if you resolve on that literal, so a clashing literal, original clause alpha prime, they have different literals, L, right, L and L prime. If this clause is not tautological, right, then this one is a witness for not being blocked. And then this is the insight which I really like. Well, you can pre-compute this upfront. And you don't actually need to, this is on a second slide, you don't need to actually change anything when you have learned clauses through like CDCL or something. Actually, you can completely pre-compute this only on the original clauses, like all the possible reasons why a certain clause on one of his fixed literals is not blocked, right? And there will also not be that many. I mean, there will be only as many as there are literals, as there are literals occurrence in the maximum case, right? So let's assume we have these guys, for instance, gone. And these guys here, by the way, because they were blocked, for this is what I said before, these two are blocked because the Y1 only occurs in these two, and they are clashing, right? They, of course, can be removed because they're removed on this, because we have a blocking literal Y, right? We can remove them. So we can quantify over this Y's, right? So I can actually remove them globally. So I don't need to do it dynamically. I can do it upfront, right? But I cannot remove this clause, which I used before when I did this block set, right? Because that one has only here this one. What was it? This one here? No, this one, the 3, as a witness. Sorry, as a potential resolution candidate, right? But you would need to resolve here over the, I forgot again, over x1, right? Or x2, it doesn't matter actually. Okay. And this is a variable on which I actually want to project. So I want to keep that variable, and that I'm not allowed. This is the point. Right. So globally, I can remove them, and now I'm starting my kind of DPLL. And all right. Okay. Now comes the most technical 2 slides, so this is the way how Jean-Marie implemented this. I try to explain how this works. So what he pre-computes are these triples, which you see here. And this triple, here's the like template for it. They capture exactly what I said on the other slide. So these triples are kind of, for this clause alpha, if this L is in alpha, right? If this set of clauses here are all counterexample that this clause is blocked. Okay. So once again, the C here is a set of clauses such that if I resolve this clause here, in which this literal occurs with this alpha prime, then I get a tautology. So then I do not get a tautology. This is why a counterexample to being tautological, and therefore, so I have all these triplets where are kind of counterexamples, right? and I can pre-compute them. They look like you see here at the bottom. So for instance, here is one which has, so this clause 6 here, if I resolve this clause 6 with this, with respect to literal y2 variable y2, then these two clauses here are, sorry, these two clauses are a counterexample that this guy here is blocked. So 6 is blocked. Let's check this. So clause 6 here has this y2 in it, right? And then clause 5 here and clause 11, then you can resolve them with 6 and they would not be tautological, right? And so you pre-compute this and you watch then here the clause, which is a counterexample, right? So the clause 5 is watched. If it's in this set here, C, and it's a counterexample, so if this clause goes away, right, then you need to check, well, right, if 5 goes away, you would need to check that 11 is also still there, right? Because if it's not there, then 6 is blocked. This is the idea. Okay. So this is what you pre-compute upfront, and now we can start sort of the simplification. So if we now do an assignment to a literal, so I think the next slide, if I'm setting here now my x1 here to true, which was the, in my DPLL, I do a branch, right? And then this closed clause goes away, right? And then actually turns out that these three clauses here become satisfied, right? Like 1, 6, and 9. And because of that, actually 11 should be removed. And how do I detect this? I don't have this code on the slide. It's in the paper. Well, I need to kind of update these watches to maintain this invariant I was saying, right? And while you update this, you will figure out, oh, there is no clause left for this particular one. And then you found the blocked clause. And then, of course, you have an additional propagation queue, not just the propagation queue for literals, which became true. You also have a propagation queue of clauses which became satisfied, right, or blocked. And then you just continue through this queue, you update those watches, and that's it. And then if you think carefully, this also gives you a nice, this is backtrack free. This is how the term we used. Well, because you maintain this invariant, and at the point you figure out there's nothing left, well, you keep the watch in there, and then when you need to backtrack, right, you will just get it sort of back. Yeah, so I should say there's an additional flag which is called activated. So clauses are activated or not activated, and when you do this update to these watches, you need to check whether clauses are activated or not. All right, so this is quite nice. It's not, it's of course more expensive than doing this pure literal version I explained to you. So pure literal, really each clause here has is watching only one literal, right? But here we might have like, yeah, he also in his slide we might here the clause 10 here it watches here clause 7 and clause 5, right? All right, and let's evaluate this. So Jean-Marie took the 500 instances he had. Actually, the model counting competition has 200 every year, but the ones from last year were not available at the time of the paper was written. So he only had like from last year 100. And I should also say D4 is, as we saw, I think in Christoph's talk, so it's like one of the top performer in the competition. So it's like, I think it was consistently in all tracks, yes, last year, number 2. So actually, like the experiment was only comparing against the D4 itself. Next slide, there is a table. And so I need to explain, you see, this is the obvious thing. Remember, we had these 3 clauses sitting here, which were globally removed, right? Because they would be blocked with respect to this variable over which you quantify, right? That's our P version here, this preprocessing version. And then that one is both the dynamic version and the P version, right? And let me show the results. Yeah, so this dynamic version, well, I think the I is still from in processing, but I'm responsible for the title and I changed in processing into dynamic block clauses. So this should be probably in D here. This means this is the dynamic version because it's also, of course, the largest number of instances. And the preprocessing is barely useful, right? Actually, doesn't solve anything more. This is kind of what I would have expected too. So that's why I never considered that, right? And but Jean-Marie had this idea of making it dynamic. And in the next plot, you really see this is quite substantial, right? This is a huge improvement. You want to have these plots in papers, right? So this is quite cool. Okay, so see the baseline version versus the one with the preprocessing and this dynamic, right? One thing you might say there's one potential caveat here. So if you know how these model compilers work, right? So they do this DPLL on top, and then they get a CNF, and then they check whether the CNF has been seen before in the cache. And if it was not seen, then it's put into the cache to not be counted again, right? And now, of course, block clauses would only would help you to shrink the CNF. And maybe only this lookup in this cache, which is actually bottleneck, is the reason for this improvement. Now, this slide shows that this is not the case because this is the number of blocked clauses eliminated over. Sorry, now I think I have the wrong. I have the wrong slide. I thought. I think yes. So this is the number of decisions made in the new versions, where the number of decisions made in the old version, and you see there's way less decisions. So it's not just like the effect you get by putting smaller CNFs into the cache. And last but not least, here is the that's what I wanted to say, the percentage of clause deletions per decision, right? So this is what you see on the left, and you see quite some variance here, but you also see an effect. So it's not just that sort of you have very small and very large numbers. So this is quite interesting. So in some cases, you get one decision, you have 10,000 clauses removed. So this is also quite impressive. So this is a very nice technique with lots of effect. All right, so conclusion. So it's sound if you're doing it on these variables which are quantified. We have a new data structure, like similar to the one for pure literals, but an extension of that. The experiments are pretty convincing, I would say. Now, what could we do on top of that? We can consider other proof systems here. Would be maybe quite interesting. One thing, this was just without change on the decision heuristic. So maybe we want to change, like we want to specifically pick variables in the decision which would allow more block clause elimination. For instance, we pick those where the variable occurs most often in those counterexamples, right? Or this counterexamples for tautology. I think this would be a very cool thing, like trying to apply this on QVF dynamically. Combining this somehow, the definition version Jean-Marie had with this block clause elimination, this is also interesting future work. So thanks you for your attention.
Questions? Yeah, Robert.
Oh, sorry. Yes, I'm not sure I understood the dynamic part in the following sense. Is this equivalent, logically speaking, with respect to be able to detect the blocked closed on the corresponding residual of the formula during search?
Yes, exactly. That's exactly.
Okay.
So this is complete in a sense, right? So
Okay.
that's. By the way, this is like unit propagation, also confluent, which is interesting. So unit propagation is confluent, particularly for this DPLL top, right? There's no. This is also confluent. So actually, every node has a confluent sort of minimum, sort of a unique minimum.
Okay.
No matter how you do it.
Okay. Thanks.
did I understand from the scatter plot correctly that there were actually no real instances where using these block clauses were negative? Yeah,
Exactly. This is quite surprising, actually. So we'll see how it fares in the next competition.
Well, I guess this may be a silly question from an outsider. I don't work on this, but in model counting, can you solve the problem incrementally, say with assumptions?
I don't think
And if
anybody
yes,
has the incremental model counter, does it? There are other people doing. There was a model counting workshop, but I don't think there's any incremental model counter.
okay, but if there was, would this technique break it? You applying it there?
Well, you would need to recompute these witnesses probably.
Okay.
Yeah, that for sure. I mean, that's a nice thing here that you can pre-compute these potential witness triples, these triples which are candidates for counterexamples for blockness.
So if there are no further questions, let's thank Armin and all speakers of this session again. Thank you.
No, I won't repeat that. Don't worry. Tea is served just outside. Please remember we have a banquet today. Shuttles will leave after the last session, let's say after 15 minutes. And also, please don't forget there are whiteboards and markers placed everywhere if you want to have a discussion, if you want to discuss something. And last but not the least, the next session chair and the speakers are requested to please contact Abhishek and his troops.
Okay. I think it works, right? I think it works, right? See? Hello, hi. Okay. Do you want to try this out now? Okay. Just, I mean, can you hear me? Yeah. Okay, thank you.
Trying. Okay. Does it work? Yeah, I think it.
Name you have to lock.
Like, okay.